Here, welcome. I hope you will enjoy the training event. Many thanks to all the people that helped in preparing this event. Staios at the back, he's the heart of this event, and of course Miria and Panayota and Andreas and many other people that you will see later today and tomorrow. So this first presentation is supposed to be about not only large language models, but Michalis will talk about also more broadly generative models. And for those of you that, is there anybody that has not used ChatGPT yet? Okay, so for those of you that maybe are online and you haven't used it yet, you can do very interesting and nice things, such as I wrote a welcome note for this event just by giving the URL of the event, which is only the agenda. And as you can see, it came up with something that I wouldn't be able to write myself because it sounds way too excited, and I'm not like that. But it basically says, you know, dear esteemed participants, a warm welcome. You can read basically what it says, right? And all of that was written by a statistical model. So as you know from the news and from everything, basically, everybody's talking about large language models today. There is a frantic progress, right? I mean, every day there is a new model, a new chatbot, a new a model that creates images from text, video from text, maybe humanoids from text very soon. And as you can see, there are many different companies involved. Pretty much all of this started just in the last 3 years. In the y-axis, you see the number of parameters, at least for those that we know. It's going up incredibly fast in the billions of parameters. And of course, there is excitement, but there is also fear. Now, this talk will not be about some specific models or some specific chatbots. I will not tell you how ChatGPT works or how GPT-4 works. I wish I knew, actually. But we will see basically which are the underlying ideas and the key technologies behind all of these models, right? So we will look under the hood to the extent that we can. So what is the underlying problem that all of these things are trying to do? They're essentially solving a machine learning problem, which is called sequence to sequence mapping, or a more fancy term is sequence transduction, right? So you're transforming an input sequence, think of it as maybe a prompt, or it may be a sentence in one language. You're transforming that into another sequence, maybe a different language, or you summarize some text, or you are answering a question about some text. Now, statistically, this can be described in very high-level terms, of course, as that I'm giving you a sequence X, which is your input sequence, and you have to generate an output sequence of a given length. You know the alphabets from which the inputs and the outputs are coming from. And as with any other machine learning model, you have to essentially learn a statistical model. You have to learn, in other words, the parameters of a statistical model that, in this case, for instance, it can predict with some probability the next word or token, if you like, from all the previous outputs that you have generated, plus the input that you received, right? So it is important to understand here that both the input as well as all the previous outputs that you generated are used in predicting essentially the next word of the output. So in some sense, you can think of this model as autoregressive, and keep this in mind when we reach the end of the talk. Now, as with any other machine learning model, you're basically learning these parameters from data, and you are you will basically go through this data multiple times. You will make mistakes, and every time you make a mistake, you go back to your model parameters, you tune them, maybe using the backpropagation algorithm, right? And the magic of the whole thing is that if you do this many, many times, you come up with a model that can actually work, not perfectly, not optimally, and you cannot actually prove that it works well, but in most of the cases, empirically at least, we find out that these models work pretty well. Now, in the case of large language models, what kind of tasks are we using? There are some self-supervised tasks. For instance, I can take your input text, I can delete some words from the model, so the model doesn't know these input words. And I'm asking the model to predict what these dark words are, these dark spots are, right? And if the model can predict correctly, then it's good. If it cannot predict correctly, it has to go back and adjust its parameters until it can, as we say, reduce, right, the loss function sufficiently. So this is a self-supervised task in the sense that you don't need an output, right? I mean, in some sense, the output is the words that you're missing. It's, as we say, a self-supervised task. There are also supervised tasks like translation, or in this case, just classification, where I give you a piece of text and you have to tell me whether the topic is biology or something else. Okay, so we will come back maybe to these different tasks later, but keep in mind that this is how we are going to learn the parameters of these models. And we're talking about, billions of parameters. So we will need actually billions of text, right, in order to train these models. Now, a very brief history of NLP, of natural language processing. Basically, the field started, of course, with the beginning of AI, but it was based on rules and symbolic processing, and those things do not really manage to deal with the complexity and the ambiguity of human language. Statistical methods came into the picture in the 80s or so, and they were based on very simple things such as n-grams, bigrams, trigrams, and hidden Markov models. Again, very limited in terms of what they can do. When the internet came up, we started collecting large data sets for text, and so that helped a little bit. But the machine learning models that were used at that point were based on Bayesian methods, SVMs, and so on, and those things do not know how to learn features, right? So the features were basically given in some sense as input, and that, of course, limits very much what these models can do. And in my opinion, even though this is a subjective statement, where we are right now can be traced back to a seminal paper by Bengio. Like in many other areas of deep learning, everything started from Bengio, in my opinion. But anyway, this paper kind of started the field of using essentially neural networks for NLP. So if we look at all of these different models, what we will find out is that all of them use transformers and the concept of self-attention. So most of my talk actually will be to try to explain to the best of my ability how transformers and attention works. And if you actually try to read this paper, you will find out that the topic is not trivial, and especially this paper is not doing a very good job in explaining it, but let's do our best. So let me first explain what attention means, in this case, self-attention. Imagine that you have the statement, the monkey ate that banana because it was hungry, okay? So, of course, we know very well, because we're humans and we have all kinds of context in our heads, we know what the word eat refers to, right? It refers to monkey. But if you're a machine learning model and you receive this sentence, right, and you try to make sense of it in some sense, you try to, for instance, translate it, or you try to summarize it, you don't really know what the word eat refers to. Does it refer to monkey or does it refer to banana, right? So if, for instance, I was giving you the prompt, the monkey ate that banana because it was 2, and then you, the model, has to predict the next word, right? Would you say hungry or would you say sweet, right? So somehow the model has to come up with what we call attention, which essentially you can think of them as weights, right, that associate each word, in this particular case, the word eat, with previous words, in some cases also with future words, about what this word really relates to. Okay, so we will talk about how these weights are learned and how they are used by the model. It's important to understand that nobody kind of gives us these weights, right? We have to learn these weights from data, again, through the process of trial and error. So if you look at the paper for transformers, you will see this nice picture, this nice block diagram. But, you know, especially if you are not working in this field, it's really hard to understand what each of these things, you know, does, right? So the rest of the talk pretty much will take you step by step through each of these blocks, trying to reverse engineer what it does. And for the most part, I want to acknowledge that I will be using visualizations from this. It's actually a blog called Transformers from Scratch by Brandon Roher. This guy has done an excellent work, excellent job. So I think I will just basically follow his visualizations. And one interesting thing about this approach is that we will start by explaining things as simply as possible, but incorrectly, okay? And gradually, we will be revising and revising and revising until we get to the real thing. I think pedagogically, this is a better approach because we will kind of build up to what transformers actually do. So the simplest way to represent words is basically with a one-hot encoding scheme where you use a vector for each possible word, right? And for instance, the word files is 100, the word find is 010. You have the element 1 to represent the word, and all the other elements, all the other words that are not present there are zeros. So if I have basically the sentence find my files, I can represent that with that matrix where each column is this kind of special vector with only one element being non-zero, and it's a vector representing one word, right? So that's the simplest way to represent words. And let's move now to how you would go from words to sentences. Imagine that we have a language, a very limited one with this vocabulary here, and you want to represent the following sentences. These are the only sentences that can appear. Okay, show me my directories, please. Show me my files, please. Show me my photos, please. And maybe I give you a certain percentage for each of these sentences, right? Let's say that this one appears 50% of the time. So as you can see, you can easily represent all of these different sentences with a Markov chain, a very simple probabilistic model where essentially you can predict the next word probabilistically based only on what your current word is. You don't need to look at the past, right? Okay, that's easy, but does it actually work? Oh, by the way, I forgot to say that you can represent this diagram essentially with a matrix in which for every word that you are currently at, you get a prediction, a certain probability for what the next word will be. So if you are in the word my, then with probability 20%, you will get directories as the next word, files as the next word, and so on. Okay, the problem now, okay, I'm sorry. So if you want to actually make this prediction, and you are at the point where you are reading the word my, right, and you want to derive the probabilities for the next word, it's just a matrix multiplication. You just multiply the encoding of the word my with this transition matrix that I showed you earlier, right? And if you do this multiplication, as you can see, you get this particular row. Now, the problem here is that if you use a Markov model and you are only looking at the current word, right, that will not actually work always. So imagine that you have the sentences, check whether the battery ran down, please, and check whether the program ran, please. And imagine now that we are at the word run, and we're trying to predict the next word, okay? So, okay, you say, I will do that with this Markov diagram, but if you, with this Markov chain, but if you do that, you see that you can generate sentences that are actually invalid. For instance, you can generate the sentence, check whether the battery ran, please, or check whether the program ran down, please. Both of these are invalid sentences, right? So maybe we need to consider not only the current word, but actually the maybe the last two words, right? And so in that case, we would not just look at the word run, but we would also look at the previous word, battery run, program run, right? So we can do that, and then we have, for instance, that if we see program run, then the next word will be please. If we see the battery, if we see battery run, then the next word will be down. But doing this approach, following this approach, increases the number of rows in this transition matrix. Instead of n words, where n is the size of the vocabulary, we go to n squared. Okay, so this will probably not scale as we go to higher and higher order models. And we need to go to higher order models because in many cases, we are dealing with long range dependencies. For example, if you try to model the sentences, check the program log and find out whether it ran, please, or check the battery log and find out whether it ran down, please. Imagine that you are here at the word run, right? In order to understand what comes next, you have to look not at the previous word, not at the last two words, you have to go back, I think it's 8 words, right? So clearly you cannot build a Markov chain that considers all of these combinations of the last 10 words. It would be n to the 8th power, right? So instead of using Markov models now, we're switching to a different approach where we look at the current word, let's say the word run, and the previous words, all the possible previous words that may have preceded that word, right? And now we're not really dealing with probabilities anymore. You can think of each of these combinations as giving a vote, a weighted vote on what the next word will be. So for instance, if you have the combination of the word run and battery, so somewhere in the past you saw the word battery, then there is a strong vote that the next word will be down, right? But if you have the words and then run, so and is somewhere here, as you see, this gives us a weak vote for both of these next possible words. So now you can think of this matrix, the matrix that basically you can use as your, a prediction table. Again, don't think of this as probabilities anymore. These are, in some sense, the votes that each combination of input words gives for the next possible word, for the word that will come next. And as you can see, most of these entries in the table are actually, worthless, right? Because they're just voting equally for both down and please. Only 2 of these elements, the battery run and the program run, are actually informative. So now we're getting into this question, how do we basically focus on only what is informative and ignore the stuff that are not? So this brings us to the topic of attention. Attention, you can think of it as masking information that is not useful. So imagine that we have this vector that represents all the different, words that we have seen in the recent past, before the word run. So we have seen, end run, battery run, but we haven't seen actually program run. So this is 0, right? When we talk about attention, we're creating essentially a certain mask, right? We want to have a mask that will tell us that given that your current word is run, you should only pay attention to whether you have seen the word battery and whether you have seen the word program, right? Pay attention only to those 2 particular earlier words, ignore everything else. And so if you multiply this mask, which is really the key behind, the attention, together with this activities, we call them the feature activities that say which of these combinations you have seen before. If you do this multiplication element by element, you see actually that only the battery run combination has actually been seen in this case. So this means that after we do this masking, most of the elements of this transition matrix become zeros. I don't even show zeros here, right? And only the informative combinations, battery run and program run, remain. Okay, now, how do we actually do this? You know, we are using, to use the terminology of the Transformers paper, we're using a vector that represents the current word. We call that our query vector. So think of this as representing the word run. We use a matrix for all of the possible masks. We call them keys. And that basically tells us where to pay attention to. And of course, if we multiply this vector by this matrix, we get this vector, which tells us actually which specific features, you know, battery run, program run, we should be looking at. And for those of you that maybe read the paper, essentially, this multiplication that I'm talking about here is this part of the equation that you have seen in the paper. We will explain the rest shortly. And of course, we will revise all of this because it's not exactly accurate. And then how do you get the actual vectors, the feature vectors that you will use in making your prediction for the next word? You can use actually a single layer fully connected network. In this case, in the spirit of, you know, simplifying, I'm showing this, I'm showing this basically with weights being either ones or minus ones, right? So I'm simplifying how the weights would look like. And basically, what you receive as input here is what the attention has told you, right? Attention has told you that you should pay attention to the word run, program, and battery. These are the words that matter in this case. And what you want this network to learn through the process of training is that if I have seen the word battery and run, then my feature, the feature that I should use in my transition table is battery run. If I have seen program and run, then I should use this feature. And of course, you can have, in theory, other combinations, like you can imagine a combination where if you have seen the words battery and program and run, then I could actually make a different prediction. So that's what we have talked about so far, going back to the original architecture of the transformers, is a little bit of essentially what happens in attention, even though I didn't tell you most of it yet, and what the role of these feed-forward networks are. And we will revise all of this shortly. Now, one problem with one-hot encodings, as you can already imagine, is that they don't scale, right? So if I have a vocabulary with 50,000 words, which is, you know, realistic for the English language, then if I have a transition matrix where I consider the current word and only one previous word, that would mean that the number of rows would be n squared, right? So I would need a matrix that is n cubed basically size. And clearly that would not scale. I would ideally actually like not to have only one previous word, but to consider multiple previous words together with the current word. So for this reason, before we do anything else, we compute embeddings of the words, the text. What is the meaning of an embedding? You can think basically of mapping each word to a vector of numbers, floating point numbers. In this case, I'm just showing it for simplicity in 2 dimensions. For example, you can think of mapping the word king in this with this vector, you know, man, queen, woman. And the nice thing is, if you have this kind of, you know, numerical representation of the words, then you can do algebra in it, right? And in theory, you could make the algebra that if I take the word king and I subtract man, but I add woman, then I should get something that is at least close to the embedding of queen. Now, these embeddings, again, they are not, you know, we don't have a book that gives us the embeddings. We learn the embeddings in our training process, right? And this is kind of another visualization with embeddings in 2 dimensions. Now, of course, in reality, most of these models that we're using today, they don't have only 2 dimensions for the embeddings. They may have, you know, 256, 512 dimensions. That's kind of hard to visualize. Now, how do you do this mapping from the n-dimensional space of one-hot encodings, all the possible words, to this m dimensions, where m is the dimensionality of the embedding space? Again, as with everything else, you can think of it as a matrix multiplication, that for the word battery, you know, it's basically, if I had only 2 dimensions, this is the embedding of that word. And how do you learn this projection matrix? Again, you learn it through the training process, through many, many examples. And so we covered what these blocks do, the embedding. By the way, you see the input embedding and the output embedding. You can think of it as, if you type a prompt, right, that is the input, right? And so you have to embed that. But also the output that, say, ChatGPT generated before, right, that is also text that you have to embed somehow. But it's not just embedding the text. You have to consider the sequence, like where these words appear in the sentence. It's one thing to say, you know, oh, my queen being next to each other, right? You have to consider that, as opposed to if the words my and queen are very far apart, right? So we represent the position of the words. That will be interesting. So I tend to talk a lot, I guess. Right, so if we have the word battery, and you know, this is the encoding, say, in 2 dimensions of that word, depending on where that word appears in the sentence, whether it is just at the current position or at some much earlier position, you basically change the embedding of the word, right, to represent the location, the position of the word in the sentence. And so if you have 2 words that have very similar embedding, say, I don't know, battery and something else that also relates to electricity, if they have a very similar embedding at the beginning, but they appear in very different locations, after you do this transformation, they will go very far apart. They will not stay close. Now, of course, another thing we have to do at the very output of the model, when we are ready to predict the next word, right? We have to do the reverse transformation. We have to somehow go from an embedding to actually a specific word, right? We would like ideally to predict one and only one word. So you need, of course, some kind of matrix again that will do the opposite transformation. It will take you from the few dimensions to the many dimensions. An interesting thing here is that when you do that transformation, you don't get a one-hot encoding vector, right? You don't get just zeros and one. So you need to somehow look at this and say, okay, which element gives me the highest probability or the highest vote? So you could do this with using the argmax operator, right, that predicts the largest value. But the problem there would be that this is not differentiable. And everything in machine learning has to be differentiable, otherwise training suffers. There are also other reasons that you don't want to use argmax, because it's very greedy. It always selects, you know, the highest value, even though there may be values that are nearby. So instead, we use softmax, which is mathematically this function here. It's differentiable, and it tends to actually give you, it gives you values between 0 and 1, and it also tends to kind of focus on the highest values and bring all the other values close to 0. Now, we need to talk a little bit about dimensionality. So we already said you start with a certain vocabulary that may be in the thousands, right? That's the uppercase N. N max is basically the maximum sequence length. So when you are typing your prompt at ChatGPT, for instance, what's the maximum size of that prompt? That's a very important parameter because it essentially dictates how long is the history that you will be looking at to infer those dependencies, those long-range dependencies. And of course, you have the parameter that gives you the dimensionality of the embedding space, right? So one thing that I didn't say is that we don't really do attention only once. We have multiple attention heads, right? Think of them as operating in parallel, independent of each other, to find out these dependencies between, say, the current word and previous words. So it's not only one such dependency that you are trying to find, you're trying to find multiple of them. And there is a technicality there which has to do with the dimensionality in which these multiple heads operate in. I think I will skip that part in the interest of time. The short story is that you are doing those attention calculations in a smaller embedding space to reduce computation time. So to revisit the whole business of attention, because I told you several things before that, strictly speaking, are incorrect, it doesn't really work in this way, right? You don't have one-hot encoding vectors. You don't have just zeros and ones in terms of the mask or the key vector. These are all floating points, and they are all in embedding space. The query, because it's an embedding space, it doesn't really represent only a specific word. It refers semantically to a group of words that pretty much all of them mean the same thing. And through this attention mechanism that you are doing here, you are not just finding a relation between this word, say the word run and the word battery. You don't just find relations between words, but you are also considering the position of those words. As we discussed before, the position actually matters. And if you are doing a task like sequence completion, where, say ChatGPT, right, you give it a prompt and it has to generate some text, then an additional step of the whole process of the whole pipeline is to mask basically things that you haven't generated yet in the output, because if they have not been generated, how can you look in the future? There are some additional things here that unfortunately I will need to skip, such as why the model uses these are called skip connections. It's not essential, so don't worry if we are skipping that. Another thing I should say is that this picture actually, it's not very accurate either, because you don't have only, say, one layer, which is what's shown here or here. You have multiple layers typically in these models. But it's interesting here, for those of you that are familiar with, say, convolutional neural networks, and you know that different layers do different things, right? They learn hierarchical features. In this case, each layer is pretty much doing the same thing. Think of them as equivalent workers on a conveyor belt that try to do the same thing, but you have multiple workers. Another thing I should briefly say is that the model actually has an encoder, which processes, as you see, the inputs, and a decoder, which processes the outputs that you have generated so far, but it also considers, of course, the inputs, right? Because the prompt matters. Now, how is the prompt affecting the generation of the next output? As you can see here, the output of the encoder, right? So the encoder somehow represents a sophisticated version of the input prompt, right? So the output of the decoder is actually fitting into the attention. This is called the cross-attention module, which essentially relates what you generate at the output based on what the prompt was, right? So the reason you see two different attention heads here is that these attention heads are doing self-attention. They relate the output that has been generated so far with the next output you will generate. While these attention heads are cross-attention, they relate the input prompt with the next token in the output. Okay, so we briefly talked about this part. All right, I'm running out of time. I want to talk a little bit about the second part, which is what we do not understand yet about large language models, right? The truth is that we're in a very interesting and weird position right now because we built something that we understand, but we don't understand. So let me just give you, in the interest of time, this one example. And it's from a paper called Sparks of Artificial General Intelligence. So this particular prompt was generated by these people. They checked, they made sure that this does not exist anywhere on the web. You could not find this question anywhere on the web. They came up with it. So the question was, we have a book, 9 eggs, a laptop, a bottle, and a nail. Please tell me how to stack them onto each other in a stable manner, okay? And it gives you, of course, the right answer. It can tell you things, incredible things, such as arrange the 9 eggs in a 3x3 square on top of the book, leaving some space between them. The eggs will form a second layer, distribute the weight evenly, make sure the eggs are not cracked or broken, handle them gently to avoid dropping them. If you read the whole thing, unfortunately, I don't have time to do it now, you will see that the model, I have to be careful here not to anthropomorphize, but the model appears to understand some physics, like how these different objects can sustain weight, which of them are flat, which of them are pointy, which of them can break. So nobody really understands why ChatGPT can do that, right? The model that I described you earlier is a statistical model that can only predict the next word, okay? And it's not that OpenAI is doing something magic that they didn't tell us and we don't know. No, I mean, they also admit that they don't know how this thing happens. So I will skip this one, but the bottom line is that it also has a form of emotional intelligence. It can actually understand from this prompt the feelings of the involved people. I'll leave you with that. Now, my theory about what's happening here is that we are dealing with a phenomenon of emergence, right? Emergence is something that is very well studied, of course, in physics. And it has to do with this notion that an ability is emergent if it's not really present in small systems. But when you exceed a certain critical size, then you start seeing all of a sudden these properties that the small system didn't have. And indeed, people have done this kind of measurements with various tasks using, ChatGPT and other models, that indeed, as long as the model is less than maybe 1 billion or 10 billion parameters, nothing interesting happens. They cannot really perform these tasks. But when you exceed a certain critical point, boom, something happens and the models actually work. So this is clearly to me, this clearly means to me that there is emergence. And emergence is a very fascinating thing because essentially, if you look at the scale of things, right, how you go from atoms to molecules, how you go from molecules to proteins, how you go from proteins to things like, neurons and other cells, DNA, how you go from neurons to brains. Science is very good in working in one of these scales. For example, in neuroscience, you will read thousands and thousands of papers that talk about how a neuron works. If you ask a neuroscientist, explain to me how we go from neurons to a whole brain, they don't know, okay? I'm not just saying that because I'm not a neuroscientist. They don't know how this transition actually happens. So I think we're dealing with something similar here where we understand the mechanics of how a large language model works, but we don't understand this emergence. So to close, I think that basically, a lot of people are talking about AGI, general intelligence, right? Whether it will happen or not happen. I say it's already here. Stop, thinking about it. It's here. And this will be the greatest invention of our generation. I truly believe that. It will not be nuclear fusion or anything else. It will be artificial general intelligence. There are many opportunities for all of us in terms of innovation. And I want to emphasize that it's really, for those of you that are into science, it's a once in a lifetime scientific challenge here, and it's open for us, for our generation, right? We can actually be the people that actually understand how AGI emerges from these models. It's not something that somebody else will do. You know, we have to do it. And we have to also make sure in the process that the models that we create are safe and aligned, of course, with human values. And the thing that I find most fascinating is that in the process of finding out how AGI works, you know, we can also find out what distinguishes the human mind from AGI, right? Because of course there are differences between the human mind and AGI. And when you understand how your artifact works and what it can do, what it cannot do that, you know, a human mind can do, you really understand, in my opinion, also the ultimate question for science, which is, you know, how we work, okay? So thank you very much. And Mihaly, I hope I didn't exceed the amount of time. So the next part will be the